no. Okay, so here's what we've got today. We're gonna finish discussing the 4 fundamental forces, and that's assuming that my voice holds out. And then we're gonna begin to introduce the lab that we will kind of start today, work on tomorrow. Wednesday is a service day, and that will be due on Thursday. Yes.
Is it service day for both Mays and Mesa?
I do not know the answer to that question. I don't think it is for you guys. So we're gonna be busy, so you guys just do whatever. So we're gonna be out cleaning solar panels. So I don't know what you guys do.
Wow, your school hates the community.
Yeah, no, we don't.
Easy.
Well, our community is perfect, so.
Oh, whatever. Our community's
Our
that's
solar
such a
panels.
May South attitude to have.
Also,
really
all
is.
our solar panels are clean.
You don't have any solar panels. Trust me.
That's why they're
You
clean.
have no solar panels. Where every solar panel is in this district and you don't have one.
That's why they're
So-
clean, because they don't have any.
Slackers care about the universe.
Yeah, they don't care about anything.
Okay,
Those
anyway.
Southies.
So I don't know, I gave you guys just, whatever.
They're offsetting our solar production.
Okay,
It's not fair.
so back to our story. So if you look at this force of gravity, so gravity obviously was the first kind of fundamental force that they talked about, but the irony of gravity being like the first force is that, and we can do the calculations and it works, and we really don't know what mechanism is for gravity to work. We'll talk about that later, but Einstein had the view that space and time is warped, and when I drop this ball, it's just following a curvature of space and time, and that's the direction that it's gonna follow, because the Earth is creating this big massive warp in space and time. Eventually, we're gonna spend a lot of time with this equation. Here's all you need to know for now. Masses gets bigger, force gets bigger, bless you. If you increase the distance, you decrease the force. So if I have these two steel ball bearings, okay, they're pretty hefty, okay, right? So if I increase that distance, I'm gonna decrease that force. But if I take one of those and hang the bowling ball, okay, there's gonna be a greater gravitational force between these two because this has more mass. So more mass there is, the more force there is, the greater the distance, the less that is.
Are
Okay.
those just the thermite balls, but you took the aluminum foil off one?
Yeah,
Okay.
we'll get there. Okay. Now, the electrostatic one is ironically somewhat better understood than gravity is, even though it's more difficult to measure. So this is called like an energy tube. So if I hold one side of it and then touch the other side, I complete a circuit. So the cool thing about us as humans is that we can complete a circuit. So we'll come up here. Colin, come up here. Rashawn. Yeah, let's just make a big circle. There's only 7 of us.
Yay.
So we're gonna have a kumbaya moment, okay? Go on, Anna.
I'm not. Oh, I don't want to touch no Southies.
Oh, shut it.
You'll soil
Really?
You'll soil my purity.
Really, shut it. Okay, so as soon as I complete this and touch that, we complete a circuit. Now, Danny, look, now just barely touch that hand. Hold on. Danny, you're breaking the circuit.
Oh, okay.
There we go. Okay. Now just kind of tap. So here's the cool thing. Do that. Just kind of keep doing that. Okay. So here's the cool thing. So if you look at what has to happen, so this electric current has to circulate through all of us. It flows across our skin, and then that flows across here. That completes the circuit. Oh, instantaneous. Again, this is something that, okay, we're good. So this is something that you can't see, but yet it's obviously a field that's being produced. So when you look at this equation, and this is like the broadest of all of them. In fact, it's F equals K Q1 Q2 over D squared. So this one is similar in nature to the gravitational force. This is just a number, these are charges in the second half in the spring. We'll spend an entire unit talking about basically this equation. So, like let's say for example, you have a proton and you have an electron. You have a simple hydrogen atom. So this would be the charge on the proton, this would be the charge on the electron, this would be how far apart they are. This is just a constant, don't worry about it. But here's what I want you to see, is that, again, it's a similar type deal. If you increase the amount of charge, the more charge that you have, the more force there's going to be. Just like the more mass that you have, the more force there's going to be. Where this gets weird is there's any number of things that how it gets weird. One of them is how that is transmitted. So if you got gravity, okay, hey, you can kind of visualize space and time being warped. Okay, kind of get a visual. But if you have an electron moving around a proton, how is that force carried? How does that electron know, because it has a negative charge, that it's attracted to that positive value? Okay, space and time, you kind of visualize that as a physical structure. This, there's nothing, okay? But yet clearly there is an attractive force. And this is actually, every fundamental force has like a charge carrier or force carrier. This is actually carried by photons. And you think, oh, that's cool, right? Photons, these are the same things that are producing light. So the photons that produce light also allow the electrostatic force to be carried. So now, fast forward a little bit. So early 1900s, J.J. Thomson discovers the electron, used cathode ray tubes, similar to what we did last week. So then along comes Ernest Rutherford. Now, these guys were physicists, okay? And what they were trying to figure out is that what's the structure of the universe. So to get, and again, this is just to kind of give you some perspective. So Rutherford set up a piece of gold foil, like this. And then he had a radioactive source, and it was shooting these alpha particles out. So imagine, this is just aluminum foil, but imagine that this is just gold foil. So the beauty of gold foil is that it's very, very, very malleable. And you can work it into a sheet that's basically only 1 or 2 atoms thick, because the atoms are so sticky, so you can work it into a very, very thin sheet. So like it would be like even much thinner than this piece of aluminum foil. And so he had this set up, and it was solid, it didn't have the holes in it. I'll explain where the holes come from in just a second. And he shot these alpha particles at it. Now, and everybody has this visual, like you can see the alpha particles. You can't see the alpha particles. They didn't even know what they were at the time. That's why they just called them alpha particles. Well, later on, they figured out that it was, if you harken back to your Chem 1 days. So, anybody remember what the 4 represents?
The atomic.
Nope.
Thymol.
Huh?
Thymol. Oh wait, never mind. I'm thinking of something else.
It ends in number.
Atomic number?
Nope.
Mass number?
Mass number, which is the total number of
Protons and neutrons.
protons and neutrons. Will Stanley, what's this number? I taught you Chem 1.
Number of protons.
Number of protons, otherwise known as the blank number.
Atomic number.
God, I don't even go back and flunk you if I got that wrong. Okay, now,
F minus.
so, again, it's tough to emphasize just what happens on an atomic scale. You visualize this, and Will, you did this calculation in a density lab,
Yeah.
and we calculated how many atoms there are stacked side by side by side to make up that thickness of aluminum foil. And it's about 94,000, okay? So you've got that piece of aluminum foil, there's 94,000 atoms, aluminum atoms stacked side by side by side by side by side. Then within each atom, again, for scale, if this is the aluminum atom, the nucleus is a human hair right in the middle. So everybody says, oh, let's split the atom. It's like, it's tough to understand just how difficult that is. Now, so Rutherford comes along and he shoots these alpha particles at this sheet of gold foil. And at the time, the plum pudding model was all the rage. The plum pudding model viewed the atoms as basically like a chunk, Lego, and there were positive and negatively charged particles evenly distributed. And that made sense, okay? Because if there were electrons, there had to be positively charged particles, because of the fact that if there were just electrons, we wouldn't be here having this discussion because nothing would ever stick together. If there were just positively charged particles, we wouldn't be here. Even if you didn't have neutrons, you could not build a stable nucleus of any size because the neutrons are there to mediate and stabilize the nucleus. So you got to have all three of these particles for us to be here talking about atoms, okay? So, again, what we talked about on Friday, Ernest Rutherford was a physicist. He goes, you want to figure out what the aluminum foil is? Let's start shooting stuff at it. He chose the alpha particles. Now, he knew that they were positively charged because he took like a battery and put that on either side of this beam of particles. And what he noticed is that there was a positively charged plate and a negatively charged plate. And the particles would get deflected down away from the positive plate and toward the negative plate. He goes, oh, right, these are positively charged. Now again, he could not see them. The only way that they could know what was happening was that they had a phosphorescent screen. So have you ever seen stuff that like glows in the dark? Okay, like phosphorescent algae, which is really, really cool if you've never seen that. So phosphorescence, you have to hit it with something. When you hit it, which is a non-technical term, but you hit it and the electrons get excited and emits this green light. So the only way that he could detect the presence of these alpha particles was that it was a darkened room and he had this phosphorescent material. And every time one of these particles would hit that phosphorescent material, you would see a small flash of light. Okay, again, I emphasize this, we talk about these as particles, but it's the nucleus, it isn't the entire helium atom. It's just the nucleus of the helium atom. Now, so he's got these, he knows they're positively charged. There's a phosphorescent screen. He puts this sheet of gold foil and he begins to shoot stuff at it, okay? Now, at the time, the thinking was the plum pudding model was all the rage. But as he does this, and he has these graduate assistants, and it was a horrible thing to be in that room. Number one, you're sitting beside like thorium-238, which is very radioactive. It's kicking out these alpha particles, which have the capacity to script the DNA if enough of them hit you. You're sitting in a room that's dark, and you literally have a piece of paper, and you're making marks on this piece of paper where you see the flashes of light. It's like, oh, this is cool, okay? This is exciting. Wow, what do? I make marks on a piece of paper. But what they found was that when these particles hit that piece of gold foil, the vast majority of them went straight through. So it would be like me taking this piece of gold foil and throwing this golf ball at it. And almost every time, the golf ball just goes straight through. It appears solid, but almost every time I throw this golf ball, it just goes straight through. So I would have like a mark on the other side, and I'd keep track of where the golf ball hit. Most of the time, golf balls just get hit straight on the other side. Sometimes it would get deflected a little bit, sometimes it would get even more deflected. Vast majority went straight through. So if I threw this golf ball and the vast majority of the time it went straight through, what would you conclude about the aluminum foil?
Mostly empty space.
It's mostly empty space. It's like, did it appear solid? It's mostly empty space. Now, literally, 1 in a million, 1 in a million, that alpha particle would come in, hit that gold foil, and it would bounce back. Okay, literally, exactly like 1 in a million times. 1 in a million. So at this point, Rutherford's going, this was a huge problem. It was literally a huge problem for the scientific community. Because they're going, this is problematic. Because the only way that alpha particle, which had a positive charge, could bounce back is if it hit what?
Something positive.
Something else that had a positive charge. Okay? It's the only way it could happen. So at this point, Rutherford's going, well, so much for the plum pudding model. So now he's sitting there going, this positively charged stuff, we call it the nucleus, is extremely tiny, it's extremely dense, and the vast majority of this atom is empty space. And they're going, well, ruh-roh, Shaggy, this screws everything up. And here's the reason why. What's the problem with having all this positive charge in one small area? What should it do? It should go flying apart. Rutherford's going, this doesn't make any sense at all. Because it's hard for me to convey to you just how screwed up this became. Because here's the analogy that I would make. And I can say this because I grew up with 3 older sisters. Okay? So let's say that you have 6 girls. And they hate each other. Okay? Like they want nothing to do with each other. Somebody posted something on Snapchat, Instagrams, I don't know, so somebody's boyfriend, they wore the same dress to the 7th grade dance. I don't know, okay? But they hate each other. And they're holding, and Anna's sitting there smiling, okay? And they hold on to this grudge, okay? Guys, I've literally seen guys like literally in a locker room like beating each other. And then like 2 minutes later, you want some M&Ms? Yeah, sure, okay, cool. Okay? No, I've seen that happen.
That sounds about right.
Yeah, it does. It's like, okay, we're cool. All right, we beat each other up, no, we're good. And so these girls like hate each other. Like if they're walking down the hall, like they will go down the other hallway just so they don't have to run into them in the hall. Hate each other. However, you take those same 6 girls and you confine them into like a Volkswagen Bug. You force them into a very, very, very confined, tight area. And they become the best of friends. They're taking selfies, they're posting stuff on Instagram, Snapchat. They're doing the filter thing. Okay?
Not scientifically possible.
Huh?
Not scientifically
Oh, no,
possible.
say with the story. It's my story. It is. Okay? But and they love each other. They are the absolute tightest bond of sisterhood you could ever imagine, as long as they're in that Volkswagen Bug. You get them outside the Volkswagen Bug, guess what? They hate each other again. So here's the quandary that the scientific community faced. It's like they kind of understood electrons. Okay, it didn't have a problem with them. But the idea that you're going to take these protons that don't like each other and you're going to cram them into a very, 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 very small space. And not only are they there, but they're stable. I mean, and thank physics that they are. I mean, like I told you, I walk in this morning, I worried about a lot of things. I didn't worry about this table not being a table, okay? It's still going to be a table, right? When you wake up in the morning, you don't have to look at your hand going, oh man, my atoms changed, man, what happened to my hand? No, okay? They're stable. That's a good thing. And so it became this challenge. It was like, how do we explain this? This makes no sense. Literally, it upended everything that they had studied in terms of what should happen. So they're basically, literally, this is what happened. They said, we have to come up with a new force because the first two aren't cutting it. So, oddly enough, they came up with, it was not the most clever name in the world, but it's the strong nuclear force, okay? So the strong nuclear force, and this, I think, in my opinion, wins the name for like the best carrier. Like electrostatic force is carried by photons. The strong nuclear force, there's two things to know about it. Number one, it's the strongest of all the forces, okay? If I ask you that question on a test and go, what's the strong nuclear force, or what's the strongest force, don't miss it, okay? Literally, don't miss the question. It's the strong nuclear force. Don't miss the question.
Or it just fails the whole test if you miss it.
Oh, yeah. So,
Feel like neutron.
but it's the strongest force, but it acts over the shortest distance. So, the particle that carries this strong force, and this is what I think is the cool name, is called a gluon, okay? Because it acts like glue. So electrostatic force is carried by photons. They think the gravitational force might be carried by something called a graviton, which also has kind of a cool name to it. But the problem is we haven't been able to find them. If the gravitons exist, we're over. And then the strong nuclear force, we've actually discovered these, and these are carried by particles called a gluon, which makes sense. It's like, oh, it holds the nucleus together. It's like a glue. We'll call it a gluon. Cool. Crouton was already taken, so we really couldn't use that.
Holds
So
the salad together.
it does. That's what holds salads together. So you have, and then individual people are called persons. So if you get croutons, photons, croutons, persons, if you just take it to a logical conclusion. So at this point, they're like, man, we got to start all over from scratch. This really sucks. Now, here's where you can't apply the thoughts of what you know to the world of the atom. So at this point, though, these guys were kind of excited because, again, all of these people were physicists. They weren't chemists. They weren't biologists. They were physicists. Basically, because they didn't have any other thing to worry about, so they said, let's take on the structure of the atom. Chemists, they were worried about how Chihuahua was a rearrangement. So they said, okay, cool. So we got this stuff. We don't know what to do with it, but they said, all right. So they said, we're going to take this nucleus that looks like the sun, because these were all physicists. So they said, oh, we're going to let the nucleus be the sun, and they had all studied planetary motion. So they said, okay, hey, just like the Earth spins around the sun, held in by a gravitational field, the electron could be held around the nucleus in a similar type fashion. So they said, oh, we're just going to make the atom look like a really, 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 really small universe, solar system, where instead of the sun and the planets, you have the nucleus and the electrons. It's cool. It fit. They were trying to build this mental model of what was happening. But there was a couple of problems. One, so here's this electron that's going around, right? Electrons, as small as they are, and they are very, very tiny. To give you some comparison, if you have one proton, it would take about 1,800 electrons on the other side of the balance to equal that mass. So literally, it takes like 1,800 electrons to equal the mass of one proton. It's very, 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 very tiny. And the weird thing is that they also have, every electron we've ever studied is like the ultimate cookie cutter factor. Every electron we've ever studied has the exact same mass and has the exact same amount of charge, 1.60 times 10 to the negative 19th coulombs. You will learn that number later on, okay? Every proton we've ever studied has the exact same mass. And it has an equal and opposite amount of charge, 1.6 times 10 to the negative 19th coulombs. And that became a problem. It was like, how can these electrons, which are extremely tiny, 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 have the exact same amount of charge as this proton does, which is much, much, much more massive? So that tells them, like, okay, well, mass isn't a factor when it comes to charge. It's just some intrinsic property. And then it becomes like, well, what creates the charge? That's a whole other discussion. So they said, okay, cool. These electrons will be orbiting the nucleus like planets orbit the sun. And then everybody was happy. Great, we've got this working model. But here's the problem with this, is that if I take this and start to spin this around, eventually I'm going to get tired, right? I'm going to lose energy. And as I lose energy, this thing is going to slow down, and it's eventually going to collapse into the nucleus. Well, electrons don't do that, okay? And electrons, because they're moving in a circle, are accelerating, which we'll talk more about later. And so the electrons should be losing energy. And if they're attracted to the nucleus, which they are, it's like, this doesn't make any sense. How are these atoms stable? Why do these electrons not lose energy and collapse into the nucleus? And then it gets even weirder if you remember back to the Chem 1 days, and you all studied like the electromagnetic spectrum. And if you remember that, like here's this bright line spectrum, and you would have like red lines and violet lines. Okay, remember that? Each element has its own unique spectrum. And that became problematic. It was like, why do these electrons only absorb and emit certain amounts of energy? This doesn't make any sense either. So there was this whole bunch of weird things that were happening. Like I said, in the spring we'll talk about this, but it turns out that the reason that the electrons don't collapse is that they have to satisfy what's called a wave function. So they can only they can only exist within certain allowable energy levels, because the electrons travel in waves, which gets even weirder. So it would be like me throwing this ball to Preston, and then as soon as I let go of it, because it's moving, you would see the ball begin to travel like this and have a wave to it. And it's like, okay, well, that's going to get really weird, okay? So all sorts of weird things they figured happen inside the nucleus and inside the atom. So here's the point of the story. So they had to come up with another force. Okay, we'll call it the strong nuclear force. Not clever, but it got the job done. And then once they began to study especially radioactive decay and fusion processes like what happens in the sun, there was a fourth force they needed. It's called the weak nuclear force. Don't worry about it. I will never, I promise you, never ask you about the weak nuclear force until maybe in the spring when we're studying nuclear reactions, okay? So if it's a multiple choice test and I ask you about any of the four fundamental forces, the answer is never the weak nuclear force, okay? Unless I ask you, what's the one force I'm never going to ask you about, then choose the weak nuclear force. Otherwise, it's not anything we're going to worry about. I'm not trying to discredit the weak nuclear force. If the weak nuclear force didn't exist, we wouldn't be here having this discussion, because the sun wouldn't be changing hydrogen into helium, okay? So it's important, it's just not what we're going to study. So if you look at how chihuahuas interact, okay? So let's talk about the electromagnetic force. So this is a small scale version of something called a thermite reaction. So what I'm gonna do is I'm gonna take this, and if I barely hit these together, okay, nothing happens. You have to overcome what's called the activation energy. It's like a threshold that you have to meet. And if I hit them hard enough, then you start a reaction, okay? Oh, come on, got in. No. Oh, that was a good one. So what you hear as that explosion is the rearrangement of the chihuahuas, okay? So one of the things that we never do, we never touch, is the St. Bernards and the chihuahuas, okay? The only time that ever happens is in radioactive, like decay, or fusion or fission processes. What allows us to exist, what allows us to have energy, what allows us to have senses, what allows us to see, hear, touch, that's all driven by the chihuahuas, okay? Chihuahuas are important, as are the St. Bernards and the sheepdogs, but in terms of like your daily interaction, it's all about the chihuahuas. But now this is where things begin to get weird. So if you look at like a hydrogen atom, okay? So hydrogen, remember, is one of the diatomics. Why isn't my pen? So basically, here's the hydrogen atom. Remember the diatomics from Chem 1, like hydrogen, nitrogen, oxygen, okay? So here's the nucleus, which is just basically nothing more but a proton. And there's another proton. And you have the electrons that are moving around, okay? So here's a simple hydrogen atom. And this creates a problem, okay? It does. It creates a problem. Because what do you know about the two protons? They don't like each other. The protons are going, we're out of here. Okay? The protons don't want to be together. What do you know about the electrons? They don't like each other either. So the electrons like the protons, but that kind of holds them in their own orbit. So then it was like, how do you explain, literally, this became a problem. It's like, okay, you all are so smart, explain why hydrogen is diatomic. Why is hydrogen the most abundant element in the universe, and it exists as H2, but yet they don't like each other? You know, they don't. And then I was like, that's weird. Now, you take helium, okay? Now, if you look at helium, anybody know where the element helium was first discovered? First discovered actually in the sun. That's why it's called helium. It comes from the Greek word helios, which means sun. So they were studying the light that was emitted from the sun, and they saw a spectrum of an element that they had never seen before, and that's why it's called helium. Now, eventually they isolated helium here on Earth. So why do you think helium is difficult to isolate?
Noble gas?
It's a noble gas. It doesn't react with anything, okay? It's like at a party. Sodium, chlorine, the halogens, okay, alkali metals. If you don't imagine that you're at a chemical party, your metals and non-metals are hooked up. Hey, how you doing? Carbon's bonding with everybody. You're making water, hydrogen and oxygen reacting. Okay, you get this montage of interactions. And then you've got the noble gases that are going, so, and they're just hanging out, you know, by themselves. They don't even want to interact with each other. I mean, they're just inert. That's why they're called the noble gases. They're like, peasants, go away. I don't want to interact with you. And so that became a problem. Like, how do you even isolate helium? Because of the fact that it doesn't interact. Okay? It's like, okay, hey, you have all the people that like the Dallas Cowboys, raise your hands. Okay, you all go over there. They're interacting. We can separate them that way. Helium would be like, raise your hand, and helium would be like, no, I really don't want to. Screw you. Okay? They're not doing anything. But once they found it, and then they figured out the structure, which this even gets weirder, because if you look at helium, it has 2 protons, 2 neutrons, and then 2 electrons that are orbiting around it. Okay? So everybody says, oh, cool. we should be able to make helium. How difficult can this be? Why don't we just take a couple of protons? So the recipe is simple. You want to make helium, you only need 3 ingredients. You need 2 protons, you need 2 electrons, you need 2 electrons. It's an easy ratio, 2, 2, and 2, right? So it's like, how difficult can this be? You want to make helium for the party? Great. Let's just smash together, we'll bring 2 hydrogen atoms together, which is your 2 protons, okay, your 2 electrons. So we'll take 2 hydrogen. We'll bring them together, and then we'll shoot in a couple of neutrons at the same time. Well, voila, here we have helium. Like, do a DIY helium kit. All you need is hydrogen. We'll smash the things together. Hey, we're off to the races. No, even to make helium requires, this is why it happens in the sun. It is a fusion process. And everybody says, and maybe this will happen in your lifetime. If we get lucky, maybe in mine. But what everybody's after is of energy is called the holy grail of clean energy. And that's when you take hydrogen and you smash it together and you make helium on Earth. So the cool thing about this is that if you can do this, the helium atom has a slightly less mass than the hydrogen atom does, and that gets converted into energy from Einstein's equation E equals mc squared. So they're going, this would be cool, man. If we just take hydrogen, smash it together, we get helium, we can inhale it, everybody gets to talk funny, we have unlimited stuff for balloons, and we have clean energy, because the only byproduct of this thing is going to be helium. And it sounds simple, like, dude, all we're trying to make is, we're not trying to make gold, we're just trying to make helium. Extremely difficult to do, because these protons have such a strong repulsive force because they have the same charge. So now, this is where it goes, okay, well, how are we even here having this discussion? So you look at one of your DNA, okay? What's one of the elements that make up a strand of DNA? You all studied this in biology. Carbon. Okay, cool. So you look at a carbon atom. Carbon atom has 6 protons. So that's even sketchier, because now you've got 6 protons that are combined in here. They don't like each other. So this is why I said this is like having 6 girls that don't like each other, and you've got to force them together. So this is why they figured out, is like, where did this stuff come from? The carbon, the nitrogen, the gold, the iron, all this stuff. Where did it come from? Like, oh, well, the only way they can make it is through the collapse of stars. And it was like, oh man, that got weird. Because it isn't like, oh, we were just here. No. All these atoms had to be formed in stars. The stars had to blow up, recombine. Now, the cool thing about atoms is that, and the chihuahuas, and that's all chemistry is the study of the rearrangement of chihuahuas, is that we can link these together. If atoms didn't link together to form molecules, we wouldn't be here, okay? We exist because atoms have the capacity to link together. But here's the weird thing about atoms linking together. Once they link together, they don't like other atoms. So like if I clap my hands, it isn't like I have to worry about the particles that make up this hand becoming attached to this hand. And like I pull my hands apart, it's like, oh man, there went some of my skin. Oh, that's awkward, okay? And the atoms that make up this hand don't even like the other atoms. So this is why you can do this, okay? I don't have to worry about the atoms that make up my fingers sticking to the atoms that make up my palm. So the cool thing about the electrostatic force is that it's, number one, it's the broadest of all of them. It allows us to have light. It allows us to make toast. It allows us to have electricity. It allows us to exist because you can combine these atoms. So atoms like each other until they don't like each other. So the atoms that make up your hand like each other. They're linked together. But they don't like the atoms in your other hand, or even the ones that are side by side. So there's this balancing act between how do we hook things together to form a table, will, tissue, whatever, but yet at the same time, they don't like each other. So that became a problem, and how do you explain that? Okay, stop that camera for a second.